on our workshop on polymer synthesis characterization and 3D printing. There's been a slight change in the program. Our dean cannot participate today due to a meeting he has. And so I will start with some small introduction first of our faculty. Naprej.
Super.
Sorry, I don't work a lot with this. And so where we are now, we are in Slovenia on the top north, close to the border to Austria, which is 20 kilometers away from here. So it's the area is called Koroška or Carleton in Austria. It's a Slovenj Gradec is enkrat nazaj. Vzame nazaj. So Slovenj Gradec is a beautiful small city, which and all the municipality has something like 16,000, 17,000 people. It's a quite old city. It's very small. It's also recognized as a United Nations Peace Messenger city. That's why you can see the statue of Gandhi in the city center. And what is very famous about this city, we have the largest exhibition of and bidding of the priced timber. So this is on the picture below, it's timber, just wood. So every year, once a year, we have this huge collection of timber, and people from whole world comes and to buy some special wood, which also gets it's quite expensive, it can be. So this is also quite strong industrial environment. We have several companies here, big companies and many small ones. This is the main square in the city. About FTPO, it was established in 2006, so we are quite a young institution, and we started teaching in 2007. So it's the only higher education institution, and also in a quite wider region here in Balkan, that offers these comprehensive study programs in the field of polymer materials and technologies. So usually these programs are just a part of usually engineering faculty or something, and they are more specialized, maybe in processing or so. But we offer everything from the synthesis to processing, characterization, and so. So we teach about chemistry. We have these construction and simulation programs as well for processing. Mostly, I think. Then we teach about processing, characterization, and also applications. So why this was established faculty? Because polymers are very important. Polymers are actually everywhere, and this production of polymers is increasing every year. Except now there was a bit smaller due to Corona. Then the production level lost. So our faculty stands on three pillars, so education, research, and industry cooperation. We are trying to be good on all those three. And I think we are, I can say, quite successful. We are actually a very small group. Now I think there is 20 employees altogether, but the research group is increasing, and this year we just employed two new doctors and two other staff, research staff. So these are the founders. We are a private institution, and there are some regional institutions that actually founded this in 2006. This is municipality of Slovenj Gradec and the development agency Koroška d.o.o. There are also some companies like Gramer, Plastika Skaza, BSH, Silico, Roto, Veplas, Kopur. These are not companies only from this area, but from all Slovenia. And now this companies also covers all the fields of polymers, from thermoplastic to rubber and duramers. And there are two industrial associations, so Cluster Plastechnica and TECO Slovenian Tool and Die Development Center. And some numbers about our students. Total students enrollment now it's 119, and so far we have 56 students graduated and at the first level, and the second cycle level 38. But these numbers are increasing, and already next week we have some defendants of thesis. Numbers of employees, so now we are somewhere on 20, and it is increasing, but this actually depends on the project we obtain. Main fields that we have: materials, material development and characterization. We work something on biopolymers and also this common polymers and on composite. Something on functional high performance polymers, and a lot on the quite on 3D printings of polymers. Then we are working now also, we have one European project on this recycling of polymer. Then characterization, of course, is we're quite strong, and processing of polymers. Mostly we have extrusion and injection molding of polymers, but also we have some other equipment as well. And those who are here, you will be able also to see it in our lab. And then till now we have 4 patents, over 120 scientific articles, and these book chapters. We participate also at the conferences and various seminars and so on. And we have over 50 pieces of state-of-the-art research equipment and processing equipment. These are some of our projects which we have now. The first one is IPP Twin and Green Shield. These are twinning project. We obtained them last year. DERMCO is the one about circular economy and recycling of composites. And there are some others I would not. One special, for example, is Polyflip, which was not it was a project about teaching this using reverse flipped classroom approach on teaching these technical subjects. We, as I said, we also strongly cooperate with the industry. These are just some of our partners. Maybe someone heard about Pipistrel, which is quite famous for small airplanes, and of course my favorite, the Krakovic, for exhaust for motorcycles and so. And Arborg as well, is also one of our partners, and many others, PCCL and so. So we have laboratory for the synthesis of polymer materials. Here our most interesting piece of equipment is this laboratory, this reactor, in which we can synthesize approximately 2 kilos of almost any polymer. So this is quantity enough so we can then process it as well and characterize it. Laboratory for modeling and simulation, where the students are taught to do these simulations. And we have laboratory for polymer processing, which is in other location, 200 meters away from here. Here we have one twin screw extruder, two single screw extruders, two injection molding machines, laser engraving machines and so on. Laboratory for thermal characterization. Here a special part of equipment is this, what you see here. It's flash DSC for thermal characterization, which enables heating rates up to 40,000 degrees per second. And then, of course, laboratory for mechanical characterization. We do tensile test, bending test, Charpy, and so on. So here is the address. You can find all the data about FTPO, this website, ftpo.eu. And we'll say a few words about today's workshop. We have 42 participants registered. They're coming from 10 countries. It will take 3 days. You will be able to listen 8 lectures. In the morning, there will be theoretical part, and afternoon, experimental part. I was writing this a few minutes before, so sorry for mistakes. Well, when I started organizing and this, I had many good ideas what you should hear and everything. It's like writing a project, you know, you have to add this and this and this and this. And then when you have to make lectures, then you see that there is not time enough to for everything you had in plan. So. But anyway, I think we did what we promised. But I must say that why did we organize this lecture, this workshop? Because nowadays it's everyone works on polymers, and it's quite often we could see that people doesn't have really good knowledge about them. They are everywhere. We use them in everyday's life, but sometimes people just don't know much about it. So this will, it's not meant like some kind of getting deep knowledge, but more it will be like an overview. So you can get some, it's like introductory part, I can say. So I enjoy and thank you for participating. And now I would like to ask Svetlana.
Hello. Yes. Okay. Can we start now?
Yes.
Yes. At the beginning, I would like to thank all the participants to be a part of this workshop. Also, our host, Miroslav Huskic, for organizing this very comprehensive training. And I hope that everybody will enjoy it. And I will just shortly present you our project. Okay. Our project is entitled Twinning for New Graphene-Based Composites. in electromagnetic interference shielding. So at the beginning, I will just shortly review how the consortium was built. It took around 10 years to create a consortium of Green Shield project. It started with a very small bilateral project collaboration, and today we have a Green Shield that is actually valued 1.2 million of euros. We have a 4 consortium member and currently 26 participants. Project started November the 1st last year, and it will last until 31st October 2025. Members of our consortium are Karl von Ossietzky University of Oldenburg in Germany, Institute of Electronic, Microelectronic and Nanotechnology from Lille in France, Faculty for Polymer Technology from Sloven Gradec, which is hosting this event, and project coordinator is Vinča Institute of Nuclear Sciences from Belgrade in Serbia. All activities of the project are devoted in the 7 working packages, and a large portion of this project is dedicated to education. As you all see, partner in this project are have expertise in very different scientific fields. So they all bringing their own expertise. So we are learning from each other, but also we are developing in this way new ideas and gathering new knowledge. So today we are these 3 days we will learn all about polymers, and let's just see how these are, how this component of the research is important for Green Shield project itself. As I mentioned before, we are developing new materials for electromagnetic interference shielding. And why is that important today? We are all witnessing that development of industry and telecommunication leads to development, leads to increased number if in everyday in devices that we use in everyday life. So all these devices that are producing, using or transferring the electrical energy are also the ones that are creating electromagnetic waves around itself. And this leads to a new type of pollution named electromagnetic pollution by electromagnetic waves. Apart from this pollution with electromagnetic waves, there is one more negative impact, and that is actually electromagnetic interference. This occurrence has a very negative impact on electronic device and on the human health. So this is the reason why we are trying to develop textile fabrics and polymer composites which will be able to absorb electromagnetic waves. One more problem with electromagnetic interference is the inability of is actually working performance of measuring devices, and this is the common issue in modern laboratories across the world. And due to this interference in the measurement, they can be untrusted signals, noise. The interference can reduce the lifetime of instrument and prolong the measuring time. Due to all these factors, Green Shield will try to create new innovative material that can be explored as a protective barrier against electromagnetic shielding. The goal of the project, apart from this scientific part, is to increase scientific excellence of all consortium members, but also to improve administrative skills of coordinator institution. So let's see a little bit more what is the region of the electromagnetic spectra that is interesting for Green Shield. Yes?
You're not moving the slides.
Oh, sorry. You can see now. Okay,
Yes.
this is, sorry, this is, it was moving in my computer, but okay. Can you see now the picture with electromagnetic? Yeah, thank you. Okay, so you all know that ionizing irradiation is very dangerous. The photons have a very high energy, and they are able to break covalent bonds, damage DNA molecules, and cause many medical issues. But non-ionizing irradiation is not common for its negative effects, especially, for instance, extremely low frequency electromagnetic field frequency that are not causing thermal effect nor radio waves. So Green Shield is dealing with this part of the spectrum, focus on extremely low and radio frequencies fields, and the blocking of this irradiation. So if we look about projection for the future of future industrial development, we can tell for sure that the number of cell phone devices will increase in the next 2 years, as well as the number of implanted medical devices which are actually active, so such as pacemakers. These are all raising the concerns about the people that are commonly exposed to low frequency electromagnetic irradiation, but also people that are occupationally exposed, such as workers in telecommunication industry, medicine, transportation, and navigation roles. So World Health Organization recognized this type of irradiation as a potentially cancerogenic and classifies as a group 2B type of material, and also between the scientists there is no agreement about the effect of this type of irradiation. Nevertheless, there is no clear cause effect connection, but the reason for this disagreement might be because actually this type of irradiation probably induces increased reactive oxygen species production and oxidative stress, which can trigger many medical issues, as you all well aware. So electromagnetic interference shielding it will become one of the fast growing market in the close future. So it is estimated by the year 2027 is that this market will grow to 8.6 billion of American dollars. So there is a clear demand for this type of material, and this demand will increase with time. So what is the issue is that the current shielding material such as metals, silicon rubbers, and conductive polymers has drawbacks, such as they are rigid, they reflect electromagnetic wave and cause a secondary electromagnetic pollution, or they are very expensive. So our goal is to create lightweight, elastic, flexible, transparent, durable, and highly efficient shielding material that can be used in the clothing, but also as a device protection. And why we are focused on the graphene, as there is a large number of studies exploring many different materials, but as a shielding materials, but graphene was very little studied. So you can see that only in the last 5 years there is a growing interest for graphene, reduced graphene or graphene oxide as a shielding material. And I'm sorry, before we start a little bit about shielding, let me just show you this a short explanation about shielding itself. So we all know that electromagnetic waves are characterized by power, electric and magnetic field intensity. So shielding efficiency of some material to block electromagnetic waves is actually the sum of reflection, absorption, and multiple reflection components. And if material has a shielding efficiency around 20 decibels, this meaning that material is shielding around 99% of incident wave. So this is high enough for industrial applications. And let's see what graphene is doing. Research showed that for instance, highly ordered single layer graphene produced using chemical vapor deposition, which is actually very expensive method for produce graphene, but also method that leads to best quality graphene. This type of graphene has a very low shielding efficiency of only 2.27 decibels. This is not good enough for application, for industrial application, nor this method can be upscale. The second, other studies show that when graphene produced in the form of larger or smaller flake, but in the form of thicker samples, I'm sorry, shielding efficiency is much higher. So it goes around 20 decibels. And if the material is produced from the small graphene flakes, this is there is a little lowering in the shielding efficiency, but also material is very good, show good shielding efficiency. Then graphene was produced with very little defects, with low oxygen content, astonishing astonishing shielding efficiency of 68 decibels was recorded. Also, when dopants are present in graphene structure, such as sulfur, nitrogen, or iodine, or some halogenic elements, material shows even higher shielding efficiency. And in our Green Shield project, we will use graphene oxide and silver nanowires and produce composites that will be chemically reduced or using some specialized equipment available in our institute. And we will measure shielding efficiency. So far, we produce single silver nanowires, graphene sheet, and the composite. These are SEM images of these materials. And we produce these materials in freestanding form and measure shielding efficiency and obtain the results of 18 decibels, which is close to targeted value. But what is the issue here is with the freestanding graphene oxide films, the transparency cannot be achieved, nor this material has good mechanical properties. And this is why we invited Photopo to collaborate with us in this project to overcome this issue. So we can create the composites that can be possibly transparent, but mechanically more stable, at the same time efficient to absorb electromagnetic waves in the low frequency region. So thank you all for your attention. Sorry for not be able to put in the slideshow mode. These are our contacts, so feel free to follow us on the social network, because many other activities are coming soon. and in the years to come. So thank you so much. If someone has a question. Yeah.
Thank you, Svetlana. So, hello again. The first lecture today is called Introduction to Polymers. And here we will talk about what are the polymers, what are the classifications of polymers, and then some things about very important things about polymer like molecular weight distribution, about advantages and disadvantages of polymers, then the configuration and conformation of polymer chains, which is also very important for polymer properties, then something about physical states of polymers, and at the end we will say a few things about thermoplastic, thermosets, and elastomers. So three types of polymers which are most common. So what are polymers? If we look at this movie, Graduate from 1967, I hope you will be able to see, to hear. So, 1967, there's a great future in plastics, and it is. I mean, today we cannot imagine a world without plastics. So what are polymers? Polymers are materials composed of long molecular chain made of repeating units, so small molecules called monomers. So word polymer comes from poly, many, and meros from Greek words part. So we have monomer, and we make such a long molecule which is called polymer. But there is one more word we use, and this is oligomers. So what are oligomers? Oligomers are also molecules with monomers, but they are short, something like maybe 10 repeating units or so, depending on the polymer. So these are kind of small polymers, but still they don't have the properties of polymer. So then there is a question, when does a molecule become a polymer? So how do we know when it's oligomer or polymer? So when one typical property of polymer appears. So we usually, here I have a picture of a melting temperature in dependence on the CH2 groups. And we see that here about 100 groups, then the melting point levels off, and so we can talk about polymers. So here we are coming from gas, liquid phase, solid, but low melting point, and so about 100, then we can say this is polymer. So what are polymers actually? Beside the metals, water, other inorganic materials, actually more or less everything is polymer. So actually our bodies are full of proteins, nucleic acid, and so on. We are made of polymers. We have fibers in our clothing. Everything is polymer, even if it's natural, it's cellulose, it's natural polymer. Food, mostly, as I said, proteins and so on, and also vegetables, and so we have a lot of polymers. Elastomers in our tires are also polymers. Paints, plastic wools, everything. Actually, you see this table, it's covered by polymer, and actually the wood is polymer itself. So wherever we look, we see actually polymers. And there are some rumors that there are too many polymers in the world, and we will destroy and we will use all our oil to produce polymers, and we will run out of it because of polymers. But if you see this picture from this plastic Europe, you see that there is only 8% of oil consumed for chemical industry, and out of it, 6 to 7% is used for polymers. And the biggest part is transportation. Why? Because I think it's still the same. Marine and aviation fuel is actually tax-free. So transportation, some years ago, it was very, very cheap. Now, luckily, the prices increased a little bit. So it's not so cheap anymore to transport some cheap and bad stuff made of polymers as well, and other things too, from one part of the world to the other. However, we can say 4 to 6% only is used to make polymers, so not so much. We can say much more in other fields. So what kind of polymers do we have? We can classify them several ways, and this the most common is this. We can classify them into 3 groups. So thermosets or duromers or duroplastics, which are rigid, insoluble, and unmeltable. So once you have this duromers or thermoset, a part made of it, you can break it, but you can't do anything out of it. So the problem here is mostly recycling. Then we have thermoplastics. That's the most common type of polymer. Here, for example, your computers are made of many thermoplastic as well as thermosets polymer, but most common things that we usually work with are thermoplastic. And there are elastomers or rubbers, which are flexible, also due to cross-linking, insoluble, and unmeltable. And there is the 4th group, which is called thermoplastic elastomers. So these are thermoplastic, they are not cross-linked, but they behave like elastomers. However, we can process them just like thermoplastic. We can melt them, we can dissolve them, and so on. So here is the picture of these mechanical properties. So thermosets usually come into this rigid plastic group. But of course, also thermoplastic, if we make them in the form of fibers, they become very strong, and also they can break fast. Then this is more or less flexible plastics like the thermoplast and elastomers. Here we use very little force to stretch them for quite a lot. And thermoplastics can further be divided into crystalline and amorphous, which is also very important and determines their properties. Then we have classification according to the molecular architecture. We have linear polymers, branched polymers, and cross-linked polymers. Doesn't seem much, but the difference is very big between those polymers, and it's very important also for applications where we use them. Beside this, the most common classification, we have also other shapes of polymers which are not so common. They are more they can be quite important, like dendritic polymers, star polymers. But this polyrotaxan and polycatenan, these are more, I can say, interest of for research less than for some kind of applications. So then, classification according to the source, we have natural and modified natural polymers, and we have synthetic polymers. So natural polymers are cellulose, starch, lignin, which is becoming more and more important, then rubber and proteins, for example, cellulose. We also we modify it to make viscose, and from viscose, we have some clothes and so on. And there is classification according to degradability. We have some biodegradable polymers, which are all natural, and also some synthetic and non-biodegradable. When we come to this word bio, there is quite a lot of misunderstanding also, because we have to distinguish what are bio-based polymers. These are not only cellulose and so on. We can also make a polyethylene, which is bio-based. It's made of sugar cane. However, it's not degradable, and it's totally the same polymer like if we produce it from oil. So it's just that it comes from renewable source. And then we have also some petrochemical polymers which are biodegradable. Sometimes it's also, when we use biodegradable, some polymers are degradable only on industrial scale, not at home compost and so on. So here we have to be a bit careful when we talk about this. Then classification according to the number of monomers. We have homopolymers, which are made of one monomer, one repeating unit, and we have copolymers, which are made of two or more monomers. And here we have four types of copolymers, so random, where those two monomers, A and B, are placed randomly on the polymer chain, alternating. We have AB structure, and we have block copolymers, so one block of A and one block of B. And of course, the fourth, graft copolymers, where we use polymer and we graft this smaller, usually small polymer chain or oligomer chain of B onto this original polymers. But of course, those copolymers has very, very different properties. Although it's made, for example, 60% of A and 40% of B, the properties are very much different. So it's something we have to know about it. And nomenclature, that's also important. Usually we name them based on the corresponding monomer. So polyethylene is based on ethylene, polypropylene, PVC. So we just name, we put poly and tell what is what the monomer was. Then UPAC name, it's based on the repeating unit and real chemical names. However, I must say it's hardly used for polymers like polymethylene. That's something you will probably never hear. It's always polyethylene or poly-1-methylene, ethylene, polypropylene. It is. And then another nomenclature is based on the functional group name. So we have some polyamides. If there is CONH group, polyester is COO, CONH, polyurethane, or some vinyl polyolefins. Here I can say that, for example, if we synthesize polyurethanes, here it's sometimes actually impossible to say, for example, UPAC name of this polymer, because there are different reactions, there are different monomers inside, so we just cannot find the IUPAC name. So it's polyurethane based off this polyol, which can be polyester or ether. So why we are using those polymers? Mostly because they have many advantages. They have low density, and so everything what we make out of polymers is usually also light in weight. And this is very important, especially for aviation and automotive industry, because we reduce fuel consumption, but also other things. They are much lighter to carry than made of something else, or they can be smaller or so. Then they have whole spectra of mechanical properties. They can be soft, they can be rigid, they can be very strong, or also very weak. Whatever we need, we can actually make them, get them. Here, really, there is actually no limit, not on the lower or higher side. Isolating properties, they are usually good electroisolating material. If we make foams out of them, we get also quite good heat and sound isolation. Then they have good weather and corrosion resistance. But this is, I can say, not always true. And that's why we usually also add some stabilizers. So when we are talking about polymers that can exist in the nature for 1,000 years, well, some of them can if you put them in the ground, you know. But if you leave them on the air, they will not last 1,000 years. That's why we add also some stabilizer. Easier and faster processing with wide design of options. This is one of the most important things. We can really produce parts which are of different shapes, which in a short time, for example, by injection molding. If we use other techniques, this can take much more time and also some post-processing. Here, usually, we don't need any post-processing. Less energy consumption for parts production. That's also quite important because it comes into the price. Easy maintenance. That's also connected to weather, corrosion resistance. Also can be, but not necessary. Recycling, I already said. Thermal plastic can be recycled relatively easily. It's also not so easy. Euromers cannot be, or can. It's problem. It's not that they cannot be, but it's not so easy. However, polymers have also some disadvantages like flammability. Most of them poor thermal stability. Also, most of them we have some polymers that we can go up to, let's say, 200 degrees Celsius, even sometimes even more, but also probably not for a too long time. And tendency to degradation, as I said, especially if we leave it on in the air, on the sun, and so on. Some of them can degrade. Some are stable for decades, so no problem. And of course, those properties can be improved with various additives, or sometimes we just add some other comonomers to change their properties the way we like them. So how do we make the polymers? We make them by chemical reaction. It's called polymerization. So in this reaction, we form polymer chains, and there are two types of reactions. So chain polymerization, where we have these double bonds. They can polymerize and we make polymers. And we have step growth polymerization. Here we have two types. So addition polymerization, where the two molecules just bond together and make a new compound. And condensation polymerization, where some side product, for example, water, you see, is formed during the reaction. I will not go here into any details because this will be the topic of later lecture. One more important things about polymer is their molecular weight or degree of polymerization. Degree of polymerization tells us how many constitutive units of monomers form this polymer chain. And usually when we talk about polymers, we always talk about the average molecular weight, not molecular weight like for small molecules. And here we see that every polymer usually is made of several, many molecules with molecular weight distribution, and then we calculate what is the average degree of polymerization or molecular weight. So molecular weight of the polymer is usually equal to the product of degree of polymerization and the molecular weight of this repeating unit, so monomer. So types of molar mass averages, so molecular weights or molar masses, whatever you prefer. We have 4: number average molar mass, weight average molar mass, viscosity, and Z average. And usually number average molar mass has the lowest value, then viscosity and weight average molar mass. Z average, I must say, by 30 years of my work of polymers, I've never came across this molecular weight, so it's not very often used, I must say so. How do we calculate? So here for Mn, we calculate the number of molecules with specific molecular weight, and for weight average, we calculate weight fractions of molecules with specific molecular weight. So here I have a kind of examples of how many chains we have, average molecular weight, and then we see that Mn is 76,000 and 93,000 is Mv. There is one other important thing, and this is molecular weight distribution. So it's quite important, especially from the part of processing, what kind of distribution of molar masses, molecular weights we have. So this the distribution, it's called dispersity, and it's signed by G. And before it was called polydispersity index, PDE or PI. And here we see molecular weight distribution of three polymers with the same weight, average molecular weight. But of course, those polymers behave totally different when you process them. So we have some, according to the distribution, we have some narrow distribution from 1 to 1.5. These are very usually, when it comes to 1.05, 1.11, then it's very we can make them by very special techniques. Then the normal distribution is approximately around 2, and broad distribution is about 2.5. Sometimes we need this distribution, something like 4 or 5, but then usually we don't produce this kind of polymers with this broad distribution, but we produce several polymers with some with small molecular weight, some with higher, and then we just mix them together. And so we get the polymer with a very broad distribution if we need it. So why is this important? It's as I said, processing. Usually, we have we have polymers with high molecular weight. They are more viscous, and so you cannot really sometimes process them by injection molding. They are good for extrusion, for example, and but here about the viscosity rheology, you will also hear more in tomorrow's lecture. So the properties of polymers are actually affected by both molecular weight and also by molecular weight distribution. Usually these polymers that we can buy, and so have generally molecular weights from 10,000 to 1 million. Usually it's a few tens of thousands, something like 100, and so. And also this, what was already shown before, here is glass transition temperature, how it changes with molecular weight. So in this range, we have some kind of oligomers, and at the end, this doesn't change anymore. There is another figure about mechanical properties for polymers, thermoplastic elastomer. So with different molecular weights of 47 to 367,000. And here we see very different behavior of those polymers. So the biggest the molecular weight, the more the stronger is material, but however, we cannot stretch it so much. Yes, now I said that properties are usually increasing, as we saw there, by molecular weight, but this is not always true. Sometimes this properties changes to the certain value, and then they drop a little bit back down, but usually I must say not much. But it is because of the entanglement of polymer chain at high molecular weights is what it causes this. The mobility is reduced, so sometimes also the crystallinity cannot develop due to big molecular weight. Another important thing is configuration or tacticity. There are several types of this configuration of atoms in polymer chains. So tacticity describes the relative stereochemistry of atoms in adjacent structural unit within the macromolecule. So we have this isotactic polymer, and if you're not a chemist, this air is now looking out of the plane. So here we have symbiotactic, when this side chain is one looks here out, and another one looks inside the plane. So they are changing in, out, in, out. And atactic polymers, it's when this is random tacticity, and so this polymers also changes their properties by this toxicity quite a lot. However, usually no polymer is completely isotactic or symbiotic. There are some shorter sequences also. There is always some atactic inside. And so by regulating how much, for example, isotactic part we have in a polymer, we can also regulate the properties of these polymers. For example, one important property, atactic polymers are not crystalline. Usually they are amorphous because they don't have this long chain which could find the same conformation, we will come to this, to crystallize. Then we have some anomalies during the polymerization, like we usually have this head-to-tail configuration. So it's this is kind of normal polymer. However, sometimes we get also head-to-head configuration, two radicals just joined together, and we have this. And this also influences the properties, such as, for example, in polymethyl metacrylate, this is the most thermally unstable part. So it degrades somewhere like 160 degrees. Otherwise, PMMA is stable till 200 and something. Then we have another configuration, so it's cis and trans. So when we have monomers with double bonds, we have cis or trans, we can get cis or trans configuration. So cis is when this bond goes on one side, propagate on the just one side of the this double bond, and trans if it goes trans from down up. And also here, no polymer is usually 100% trans or cis, but this is also very small difference, we can say, but it makes a lot of change, because sometimes this kind of polymers can also crystallize if you stretch them or so, but if they are cis, they cannot. Fumaric and maleic acid are two acids which are used in painting industry, coating industry, and for unsaturated polyesters. And usually maleic acid is used for this normal unsaturated polyesters, but fumaric acid gives somehow better properties. So it's usually used for a gel coat. So for this shiny part of products we can see made of this unsaturated polyester. So very small change in the structure, but big change in properties. So here is one example of polymer having different actinities and isomeric configuration. It's polyisoprene, so this is the molecule of isoprene, which has two double bonds. And we can use various catalysts and synthesize various polyisoprenes. So we can have 1,2 addition, 3,4 addition, 1,4 addition. So here we have cis and trans. There we don't have. And also those polymers, they are all rubbers, but they differ in properties. Here is the influence on the glass transition according to this bonding. So we go from somewhere minus 70 to up to plus 10 degrees Celsius. Just due to different bonding, although the chemical structure, if we write it just in CH and numbers, it's actually the same. The second important thing is conformation. The conformation describes the different arrangements of atoms or substances in space due to a rotation around a single bond. So polymer is a long chain which is not standing still. It's moving all the time. About the glass transition, for sure, it is moving, so it can rotate. And this rotation, various position has various different energetical states are different. So here we see that trans has the lowest energy of all. So theoretically, it would be the most stable trans configuration of polymer, so one long extended chain. However, it is not. Usually polymers are not in the form of extended chains, but a kind of random coil. Yeah, this is a random coil. But why is conformation actually important? Because conformation depends on temperature, and we can change during the processing. We can change conformation. We can change the. We can use the temperature range for example, for injection molding, which enables the polymer molecule to go into the right conformation so that it can crystallize. However, if we don't want it to be crystalline, we just change the properties. So we don't give the polymer time enough to come into the preferred conformation to crystallize. This is one example is a PET bottle, plastic bottle, which is usually it's amorphous. We want it to be amorphous, and PET actually it's a crystalline polymer, but by adjusting processing condition, we can make it amorphous. So now we came to physical states of polymers. This is about morphology. We have amorphous polymers, semi-crystalline polymers, and sometimes we also make these crystalline polymers oriented. For example, if we stretch it, we get oriented structure, which of course changes again properties. Some polymers are completely amorphous, and there are no polymers completely crystalline. Usually they are all semi-crystalline. We can change this. We can come sometimes close to 100%, but usually we cannot really reach 100% crystalline structure. Usually this, as they say, 100%, they are made just from the solution. It's just for research of crystalline structure in some things. If we use very dilute solutions, we can then crystallize some polymers in the, let's say, almost 100% crystalline form. There are two important transitions which we have to know, and this is glass transition and melting transition. So glass transition is a transition that every polymer has. It's below this temperature of glass transition, polymer is rigid, molecules doesn't move, conformation of molecular chains is fixed, more or less fixed, I can say. But above Tg, the molecule starts to move, and so they become they're not so rigid anymore. They don't break so easily, and so once we came over the if it's amorphous polymers and we go above Tg, it becomes soft, more or less. So at a certain point, we can also process it. But if we have a semi-crystalline polymer above Tg, it's still not soft because these crystals are still keeping the form of the product we have, and if they give them still good mechanical properties. But once we go above the melting point, the polymer also behave like amorphous about the glass transition, becomes soft, and it can flow, and we can process it. So both glass transition and melting temperature, increase chain stiffness due to if we have some bulky side groups or some polar groups in the main chain, like polyamides. Here is this hydrogen bond can be formed, and this also adds to increase those temperatures. And the melting point is affected by regularity of repeat units. So that's what we were talking about by configuration. So we have good configuration. We can enable crystallization. If we have more this atactic structure, it becomes amorphous. Usually these atactic polymers like polypropylene, they are not of very much of use, but they are still can be used as a kind of plasticizer or so. We use them. So what kind of polymers are amorphous? So polymers with large substituents like polystyrene, polyvinyl chloride. So it's a main chain, and we have some substituents below, and this prevents this chain from crystallization. Then if we have some rigid aromatic structure in the backbone, this will also make molecule more rigid, and it's harder to find a good conformation to crystallize. It's actually prevented, like polycarbonate, polyether sulfone. These are high temperature polymers which cannot actually crystallize whatever we do. And of course, polymers with a very flexible chains like rubbers and polysiloxanes. These also usually cannot crystallize, except sometimes some if we stretch them, but not generally. Then, of course, highly cross-linked polymers. Since they are highly cross-linked, they have no freedom of movement and also no structure to form crystals. So these are some epoxy resins, phenolic resins, polyurethane. These are usually not crystalline. And also some copolymers. As I said, it must be the structure, the repeating unit must be the same, so it's then it can crystallize. Otherwise, every comonomer we add, it acts like a defect in the polymer chain and prevent crystallization. And then, depending on the quantity of this comonomer, we can have polymers with various degree of crystallinity. These polymers have some disadvantages and also some advantages. Usually they have poor ductility, but they still have good mechanical properties, and one especially is creep resistance is very good. So if we have some a product which has to be stable, although it's mechanically, for example, pressed or something, and we need it to be in a stable form, it will we can make it or cross-linked or by this amorphous polymer, depending, of course, on the strength we need. So what kind of polymers are crystalline? Polymers with sterile regular structure. So we have to have linear chains which can find easily this conformation to form crystals. Here we have Teflon and polyethylene. Teflon is polymer which can crystallize, I think, something like 90%. The highest degree of crystallization under some normal conditions we obtain with Teflon, polyethylene, depending also on the structure. It's always crystalline. Then polymers with geometric isomerism, so molecular symmetry. Polyvinylidene chloride with 2 chlorine atoms. It's crystalline. PVC, if there is just 1 chlorine atom, it's amorphous. The same is for polyisobutylene. This one can crystallize. And of course, crystallization is favored by secondary forces, as I said, especially these hydrogen bonds and van der Waals hydrogen bonds are these strong secondary forces which we can obtain in polar polymers like polyamides or also polyesters and so. Applications of semi-crystalline and amorphous polymers. Amorphous polymers are used below the glass transition mostly. So, for example, plastic glasses, which we have, or mostly now we must not have it anymore almost. They have glass transition around 100 degrees, so we can still put some hot water there, and they are used below this glass transition. Then semi-crystalline polymers are used below or above glass transition, depending also on polymer, and somewhere up to the melting temperature. Not really up to the melting temperature. Usually it's a bit lower, 20-30 degrees at least. And elastomers are used above glass transition because we want them to be soft. And of course, below the temperature of flow or degradation. But we must say that thermal transitions are taking place in a wider temperature range. Sometimes it's quite narrow, sometimes it's wide, depending on the polymer. And so we can use them maybe to be on the safe side, at least 20-30 degrees below the glass transition. But this, of course, depends mainly on the size of the load. So, for example, if we have, like I said, plastic glass, we add hot water inside, we come very close to the glass transition. But since it's not, there is no load actually, and usually it cools quite fast, so it will stay. But if we have a load, like shown here on the picture, if we have high load on the material, it will deform at a higher temperature. So that's why those temperatures are, especially glass transition, is a very important property. So now we came to the last part, and we first will talk about thermoplastic polymers. These are polymers that become pliable and foldable at a specific elevated temperature and solidifies upon cooling. That's how we make products out of them. So we heat them, shape them, and then we cool them, and we get desired property. Theoretically, we can melt them and recast them indefinitely. So, but practically, we always face degradation, which is present at heating, and this degradation also changes polymer properties. It is observed that sometimes there's polymers, we can remelt them and reprocess them maybe for 2-3 times, and then they can be still used, but maybe for not so demanding applications, due to the degradation. And also, I must say that we usually add some stabilizers to stabilize them for the processing, or also for the use. For example, some UV stabilizers we add so they can withstand this sun and light generally. And I must say, a vast majority of polymers are thermoplastic. So mostly what we use, these are all thermoplastic materials. And if we look, we have three types of polymers, thermoplastic polymers. There are some standard or commodity polymers. These are polyethylene, polypropylene, polystyrene, PVC, and PET. These present the biggest part of all polymer market. So mostly what we see are those polymers. However, there are other groups. The second group is engineering plastic. Here we see somewhere like something like 10% of all. These are polycarbonate, polymethyl methacrylate, which is plexiglass, some polyamides. We make, for example, fibers out of polyamides, carpets, also many parts in automotive industry. And so these are polymers with usually much better thermal and mechanical properties than these standard or commodity polymers. Of course, here we see some polypropylene, of course, and PET. They are also quite good in mechanical properties, but they are relatively cheap. That's why we use them so many. And at the peak, here we see high performance polymers, polyphenylene sulfide, polysulfone, and PEEK. For example, these are not produced and used in large quantities. These are polymers for very specific applications where price is no question, because some of those polymers, they can cost up to 100 euros per kilogram, for example, PEEK. And so we really need them where their properties are really needed. So these polymers usually have very high glass transition temperature, so about 150 to 100 degrees or melting temperatures, and so they can withstand very high temperatures, rough environment, also they're chemically stable, and so on. So even if the price is high, there is still a market for this kind of materials. So what is the difference in properties between amorphous and crystalline polymers? Amorphous are transparent and crystalline are opaque. So if we see something transparent, we can usually say it is amorphous polymer. However, it's not always true. If we add some nucleating agents in some polymers, for example, nice example is polypropylene, we can have crystalline material which is also transparent, because the crystals are so small that they do not scatter the light. Then amorphous polymer has low solvent resistance, because amorphous polymers have a lot of empty space between the molecules. So it's a lot of space these solvents can enter in, and they can form bonds with, for example, they can dissolve polymer. While crystalline polymers have high solvent resistance, because crystalline structure is dense structure. So the small molecules cannot easily enter the crystalline structure. they can enter this amorphous part as well and slowly dissolve it, but it will take much more time to dissolve crystalline polymer than amorphous. The same goes for chemical resistance, the same reason. Small chemicals can go into amorphous polymers and attack bonds and destroy it. Amorphous, weak or strong, this we can agree or we cannot agree because we have some amorphous polymers also which are very, very strong. But generally we could say amorphous are of lower density than crystalline because crystalline structure is more dense. And amorphous, as I said, there is plenty of empty space between molecules. And due to this empty space, high gas permeability is also for amorphous polymer and low permeability for crystalline polymers because this, again, in crystalline polymers, these gas molecules can penetrate into amorphous space and then it has to go around those crystals to penetrate to the other side. And shrinkage at processing, this is sometimes also very important. This crystalline polymers has a high shrinkage at processing. And for some special application, we really need parts with defined dimensions. And there, then we use polymers which doesn't shrink a lot. Of course, they have to have also good properties. Applications of thermoplastic. This is also from Plastic Europe. We see that something like 40% of all thermoplastic we use for packaging. And there is a strong tendency to reduce packaging. You will very often hear that we should use less packaging materials. But I must say that I agree with this. Generally, I agree. But sometimes we must be also careful. For example, if we pack meat into polymer, so vacuum packing, the meat is stable for much longer time than without it. We just use it like this. And of course, if meat is packed in vacuum, for example, we don't need to look at the date of expiration because as long as the vacuum is good, the meat is also usually good. So even sometime, if it's 2-3 weeks later after, you should throw it away. If it's vacuum, it's safe to eat it, no problem. And that's why we save a lot of, I can say, food just based on this, that we use polymer as packaging. But however, there's also some things we don't need to pack everything into polymers. That's also true. Then building and construction, we use something like 20% of polymers. And here we see mostly PVC, polyethylene, high density, low density, and polypropylene. Here we use, for example, PVC. Some windows, plastic windows are made of usually of PVC, and some various tubes for drainage, for sewage. It's made of tubes, so usually based on polyethylene, high or low density. Then automotive. So although we have many cars and they are made out of more and more polymers, we spend less than 9-10% on these cars. But here we use more this engineering thermoplastic, although this polypropylene is also due to good properties. It's also very much used, also polyethylene. Agriculture, this is mostly polyethylene and polypropylene. It's used household and others. So 60% of all thermoplastic that we use goes for packaging and building and construction industry. So the next group of polymers is thermosets. These are usually low molecular weight resins which react on heating, or if we add some catalysts, like for example some acids, they can react and they form a solid, unmeltable and insoluble product. They are heavily cross-linked, so the structure is like this. No big chains, linear chains between two cross-link, very stiff. And usually we use them as a composites. So mostly some short or long fiber composites. And the types of polymers we use, epoxy resins, which are somewhere on this high end, I can say, unsaturated polyesters, which are not so good as epoxy, but we make some bolts also from them and so on. Vinyl ester resins, phenolic resins, these are three of the same group, urea formaldehyde and melamine formaldehyde resins. And of course, silicone. Silicones are maybe not so much used as composites, but epoxy and unsaturated polyester, vinyl ester resin mostly are as composites with fibers. So synthesis of thermoset, usually we use this chain polymerization. We have monomer with two or more double bonds. We copolymerize usually monomer with normal monomer with one bond and with polymer with two bonds. So this is diallyl phthalate is one example of monomer which make crosslinks in some copolymers. But mostly make them by step growth polymerization, usually addition and sometimes also condensation polymerization, but usually it is addition. And here we have monomers with two and more than two reactive groups. So we have just monomers with two groups, we will get a linear polymer. If we add a monomer with three or more reactive groups, we will get the cross-linked, this thermoset. However, here we can vary the quantity of this cross-linker, and with this we also vary the properties of polymers, so we can change the glass transition and mechanical properties if we want to make it stronger, or it doesn't need it so strong, it must be more flexible. We just change this ratio of two monomers. Properties and application, usually sometimes they have high glass transition temperature, depending on the degree of cross-linking, I can say. They are also, they show high temperature stability, especially, for example, some phenolic resins and so on. Chemical resistance, because they are dense, very densely cross-linked. There is actually, it's hard to penetrate for various chemicals and solvents into the structure. They have good strength and they have good creep resistance. That's one very important feature. If we have something which is loaded, strongly loaded, and it must withstand a long time, we will use these thermosets because it will not creep, it will not deform by time. Yes, as I said, here are some examples. Also, for example, coatings are usually thermosets, not thermoplastic material. And we came to the last group. These are elastomers. These are polymers which go large reversible elongation under the relatively low stress. So it's elastic, as we say. And that we played with elastic when we were kids, you know. Usually they are amorphous and slightly to heavily cross-linked. So if we want these elastomers to be stretched a lot, we should not put a lot of curing agent in, because we need long chains, linear chains, which can stretch like here. If we have more these red crosslinks here, it will not stretch so much. So tires, for example, you cannot stretch them. You don't need to stretch them, better not. But if we use balloons for children's, for the birthday parties and so, this has to stretch a lot. So the cross-linking is very, degree of cross-linking is small. So this cross-linking actually enables this reversible deformation. So when we stretch the polymer, these cross-links here, they keep the molecules together. So they, until we broke them, it will keep this structure. So when we release the stress, it will come back. This little cross-linking point, they just keep the structure in this original size. There are elastomers, some unsaturated. These are, let's say, natural rubber or also synthetic polyisoprene caoutchouc. Natural rubber we get from the trees, but we can synthesize polyisoprene, which has many similar properties to natural product. There is a neoprene, which is polychloroprene, which has very good chemical resistance, and used also for some foams. Polybutadiene is resistant to wear, and that's the polymer used mostly in tires for that reason. Although also in tires you see different layers made of different rubbers, and each layer has its own function there. EPDM, this is synthetic ethylene propylene DN monomer. It's also resistant to heat, light, and ozone. So it's made of, like, let's say, polyethylene, polypropylene with a small part of this unsaturated monomer, which can be used to cure. These polymers are cured by sulfur mostly. However, we can also cure them or cross-link them using some peroxide and so on. Then we have saturated elastomers like ethylene, propylene rubber. So this is the same, almost the same polymer. However, it doesn't have this unsaturated group like EPDM. So the difference between those two polymers is maybe a few percent of DN rubber. And since this doesn't have double bonds, it's resistant to heat, oxidation, and ozone, and very good also electrical isolation. And it's acrylic rubbers, also saturated. These are various copolymers usually, and they have quite high thermal and chemical stability, and that's why they are used a lot in automotive industry. Polyethylene vinyl acetate or EVA copolymer. This comes in a variety of percentage of this vinyl acetate. So if we have something like 5 to 10%, it's actually, it will not make a difference from polyethylene if you look at it and process it and so on. But if we increase the quantity of vinyl acetate. This prevents crystallization, and above 40, we get 40% of vinyl acetate, we get this elastomer. And silicone rubber is also, there are some other rubbers which are also saturated. Curing, sulfur is by far the most commonly used elastomers with these unsaturated polymer backbones, and curing is called also vulcanization. This we usually mix elastomer with sulfur, and there are some activators, retarders, and so on, and then we start this reaction. So usually there are metal oxides, like zinc oxide. Here is very common additive for curing. Fatty acids are used to solubilize the zinc oxide, so we can spread it more easily all over the elastomer, and to make this curing also more efficient and more even all over the part. Then we have some accelerators, sulfonamides, uranidithiocarbamates, which help to the reaction to proceed a little bit faster. However, sometimes this reaction can proceed too fast, and so actually one way we give accelerators, and we also give some retarders inside, so we don't scorch the material at the end. I must say that elastomers are much more, I think, complicated materials than thermoplast or duromers, because usually you have, these are just a few groups, but usually you have much more ingredients into the final formulation beside this to obtain really the properties that you wish. So elastomers are quite a complicated materials, I must say. Then peroxide are most widely used for curing those saturated polymers. So these peroxides are this kind of chemicals which has OO, this group here, the bond, and this bond is labeled, and it can dissociate into radicals, and these radicals are then abstract hydrogen from these elastomers, and they form a radical on the polymer chain, and those two radicals on polymer chain, they can bound together, and we get cross-linking. We can use radicals, as I said before, peroxide also for these unsaturated rubbers, but usually it is not the case. So these carbon-carbon crosslinks are more thermally stable than sulfur crosslinks. So if we need some material that is rubbery and thermally more stable, we use this, but however, they also have some other bad properties as well. Metal oxide, usually zinc oxide, lead oxide are used for cross-linking various polymers. They abstract also halogens, they abstract halogens, and then they make these radicals and on the chain, and which join together and cure. There are also some other defunctional compounds like amines, diamines, bisphenols, and so on. And also the first step here usually is abstraction of hydrogen, and then double bonds are formed, and then those double bonds are cured. And there is third mechanism, it's radical cross-linking. So high energy radiation can be used to cross-link polymers. However, this is more for some specific application. It's not very common that we use radiation cross-linking to cure polymers. But this radiation can be used, for example, to make polyamides cross-linked. But to cross-link polyamides, we usually add some monomer at the end, so it's modified polyamide, and then we use radiation cross-linking. Otherwise, polyamides cannot be cross-linked. Properties, usually they are very flexible, especially without filler. If we add filler, the most common filler is char. So that's why usually their tires are black. And char also is active filler. It improves mechanical properties. So we get less flexibility, but better strength. They do not dissolve in solvents, but my swell. Swell, and it might swell a lot, depending on the degree of cross-linking. Since they are slightly cross-linked, they cannot dissolve, but they can swell, so they can take in maybe 10 or even more times of solvent than it's their weight. For example, 10 grams of solvent per 1 gram of this rubber. Application, of course, automotive industry here goes more than I think 70% of all rubbers, and also shoe industry, maybe specifiers. That's not very big, but important product. We make also adhesives. Very often are used as adhesives, and those what's the word? Sealants, yes. Dichtung, yes. So that would be all from my side. I thank you for your attention, and if you have some questions also from the people who are online. If there is no questions, then I suggest we make a stop and have a coffee break for half an hour. Thank you.
Thank you.
Thank you.